All right. In particular, we're going to deal with pulleys and free body diagrams. Pulleys and FBDs. When we're dealing with the pulley, I'm sure you came across some of the problems that you had, pulley at the edge of a table, and here's your pulley, and you got a rope to some crate right here, and a rope to some hanging mass, and this is M1, that's M2, and you've got friction, so you have a surface down here that's got a mu attached to it. Can you guys see that okay? There's it glaring pretty bad. No, we're good? Okay. And what I've shown you so far, and so here's the surface of it. All right. And from what I've shown you so far, what you would do, the traditional way of doing it is to, take that mass and take this mass and do a free body diagram for both of them. And so you take your circle, and that's M2, and so you're going to have tension pulling up, and you're going to have M2G pulling down, and this will have some acceleration. So that's M2. And then you do your Newton's second law equation for this particular problem. But they're linked because you've got a tension pulling up here, but that tension is the same thing that's pulling this way around the pulley. And so M1 has a more complicated version. M1 is going to have your normal force, and you're going to have your friction going back this way, also known as mu, normal force. And then you have M1G is the gravity for that guy, and then you have, pointing this direction, your tension, and then you set up your own Newton laws for that one also. Okay, am I going too fast for you guys, or are you with? Okay. Corey and Ashmeet, are you taking notes on this? Yes, notice that I spoke it directly into the microphone of my camera. Okay. Now, there's a way to simplify all of this. What is going on right here with our ropes? This is going to save you a lot of time, so please do not miss out on this. What is going right on here with our tension-producing rope, string, chain, whatever you want to call it, is, and whenever we have a pulley, it's the same idea. All it does is change the direction of a force. That is all a pulley does. Now, you may have some, when we get really complicated, and this pulley is going to have some mass and some inertia to it, so for when it starts to pull and accelerate, but that's, that's 2.0 when we start doing our free body diagrams and for the next unit. But right now, the rope has this tension. All the pulley does, it's redirecting the tension down or to the right, rather than if you had two things pulling on each other. But if that's all it's doing, then let's remove it from the equation. Let's get rid of our pulley and create a new force body diagram that includes all of this. And so what are we going to have? We're going to get mass 2 and mass 1 connected to each other. So now we can create a force body diagram with the two masses together. We will still have normal, M1G, friction, but because the tension that's in here is equal and opposite to the tension that's in there, we can ignore it. We don't need it anymore. But what we do have is, instead of this M2G pulling down, it is now acting in that direction. It's like we take this whole thing and we extend and we make an M2G pointing up that way, where this is mass M2G, the weight of the pulley that's hanging, the weight of the mass that's hanging down. Okay, and this is going to save you a fair amount of time rather than having to do two equations to a known, solve for t, figure that, plug it into the other thing. All right. So what we're going to do for what is the acceleration? The question we're going to ask is what is the acceleration of this system? Okay, so find. Okay, find the acceleration of the system. Well, m1 is not going to accelerate in the vertical direction. It won't. The only chance for an unbalanced force is in the direction of the tension, right? Hopefully, yeah. Good. Okay. Okay. So, all right. So we're going to set up our equations now. And so we have the sum of our forces in the x direction are going to be. Let's set our axes. That's positive and positive. Okay. So this is going to be F plus m2g is going to equal, okay, our mass times our acceleration in the x direction. Okay, I'm going to put an asterisk right here because we're going to need to come back to this because there's a little tricky part right here. The only tricky part to this time-saving device. Okay. The sum of the y's, the sum of the force in the y directions is going to equal, well, that's the trivial one. That's normal force equals m1, sorry, plus m1g equals 0. So let's solve that one real quick. Normal force equals negative m1g, and that becomes what we're going to plug in for our friction and so on. So this is what we're looking for now, right? We can pretty much solve back into that into our x direction forces. So so our friction is going to be our coefficient of friction times our normal force. Well, our normal force is m1g, and that's going to be negative, because that's negative m1g, plus m2g equals max. However, let's get back to this asterisk here. This ax is the acceleration of the system. Because it is the acceleration of the system, we have to use the combined mass m2 and m1. The whole thing is going to accelerate. So that's what we plug in here. And this becomes negative mu m1g plus m2g equals m1 plus m2 ax. And then it becomes, just a basic bit of algebra to solve for your acceleration. But just for an intellectual exercise, check out the units here. You guys can see we can factor out the g, right? So this is going to wind up being negative mu m1 plus m2, yeah, times g. And the other one's going to be divided by m1 m2, right? So those are sums of masses plus sums of masses added together. That's going to cancel out to a 0 unit, right? Or to a 1 unit, a unit. Get it? One. Okay. But we're going to be left with g, which is going to provide our acceleration units, right? So that's how. So our acceleration winds up being negative mu m1 plus m2 over m1 plus m2 g. If we remember that g equals negative 9.8 meters per second squared, then we get then our negatives are going to cancel a bit, and so on and so forth, and that we get our acceleration that will go in the negative direction and then down around the pulley. And so that's how we do pulleys with FBDs. Okay, is the trick to that. Now these, of course, do get more complicated, and that's the next example I'm going to do for you in just a moment.